thank you for everybody for coming. So I'll talk, and I don't mind if you interrupt. If we get to a point where I can't finish, then I'll say no questions. If you've got questions, I kind of prefer a conversation. So I'm talking about reliably estimating the state of an autonomous vehicle to a precision that allows autonomy in cars, which is meter level. You talk typically get different numbers, but the ideas are if we want vehicles to coordinate their actions either with each other, which is B2B, or with the infrastructure, they need to know where they're at. And they need to know where they're at to a certain precision, and they need to meet that precision with a certain reliability. And examples of why they need this, and they need a global estimate, is these pictures here, where this picture is the vehicles are coordinating with the infrastructure, and the infrastructure is trying to adapt its behavior to get the most vehicles through the streets of the city in an efficient way to minimize emissions and travel time. And so it could be coordinating. Knowing where all the vehicles are and where they're intending to go, it can coordinate the signaling within the city. And in a situation like this, where you have a set of cars driving, for example, autonomously, and something happens further down the road, the vehicles have to coordinate their actions so that, for example, this red car going around doesn't get into a bad situation that it should have known about. So it's the coordination of these different actions which requires the global behavior. And in the autonomy arena, we're kind of at an early phase. And we don't want to get into a situation like happened with elevators, where when elevators came out, there was a driver. And it took many years to get the driver out of the elevator because people didn't trust the elevator. And when the driver of the elevator first went away, people were afraid to get on. And so they have these, this is a curve from business where they're talking about new product development, and this is specifically applied to the autonomous vehicle, where we're in the establishing trust phase. And ignore the years on here because everybody puts different years about when cars will become autonomous commercially. But you're at the establishing trust phase, and if you lose trust, then it's going to take much longer to get to the commercially viable stage. And there are various factors that affect trust, and there's control and there's coordination, and those things are enabled by knowledge of the state of the vehicle, what it's doing and where it's at. And this is achieved through sensor fusion, and there's different levels of accuracy that the Department of Transportation has come up with, and roughly these are called which road, which is kind of 10 meters of accuracy, which lane, which is about 1 meter accuracy, and where in lane, which is decimeter. And you can do different things with those different levels of accuracy. And currently your cell phone is at the kind of 10 meter to 3 meter stage. It can draw a very nice picture of where you're at, but I would not drive my vehicle based on cell phone accuracy, both because it's not reliable and it's not as accurate as you think it is, even though it draws a nice picture. But the reliability is what's going to give us the trust. And we want the trust so that we don't get into situations like this. I know of 2 accidents so far with autonomous vehicles, where one was about a week ago in Arizona, and that was an issue with obstacle detection, where they did not detect a pedestrian and they killed the pedestrian. And this one is an example from Florida, and to me this is an example of not doing data fusion well, because the vehicle this is a Tesla, and it drove under a truck. The truck was in front of it. It had vision and it had radar, but they basically ignored the radar. And they drove the car almost entirely on vision. And the reason they said that they ignored the radar was that it had a problem with false alarms. That it triggered too often, saying there were things in the road when there were not things, so they basically ignored it. But in the accident, the vision could not see the truck, so it was a white truck against a white sky. And they were ignoring the radar, which said there was something there, and the person died in this accident. So, of course, we don't want this to happen. We want reliable autonomous vehicles. And so you get this autonomy by combining different sources of information together. And this is a depiction of what people imagine autonomous cars will look like, and it's very reasonable compared to the autonomous cars that are being tested, where there's a wide variety of sensors on the car. There's an inertial measurement unit, which gives you acceleration, angular rate. There's many short-range sensors, plus there's LiDAR, camera, and possibly radar. And so you get this large variety of sensors, and you would like to combine these together. And when you think this through, it's what I call a signal-rich environment. So as I started out as a controls theorist, and when you're a grad student in controls, you learn about observability. And you're taught observability, and observability is a very important thing, but at this point in technology, it's not the main issue. There's so many signals that you can easily get observability. The issue is more trying to get the best signals and to get rid of the outliers. And you can easily see that. For example, I've listed 4 different types of global navigation satellite systems here. Each one of these is designed to ensure that with very high probability you have observability. So for example, with GPS you need 4 satellites to have observability, but you can usually see 8 to 12. There's also Galileo, GLONASS, Beidou, and others, so you potentially got 40 or 50 GPS signals when you need 4. So it's not an issue of observability, it's that you have far more signals than you need. How do you choose the best? And I'm looking at it as, how do I choose the least risky set of signals to guarantee that I meet a performance spec? And that's the way when I get to the end, that's the problem that I'm trying to solve. And there are other signals that you can use. There's vision, radar, and LiDAR. And if you think about one picture, in one picture you can detect hundreds of features. That image alone with hundreds of features is far more features than you need for observability. So how do you pick the least risky set of features along with your GNSS to meet your performance spec? So that's what I'm going to be talking about. And so the idea is that we're in a signal-rich environment, and this is because sensors have gotten cheap, computers have gotten cheap, and inertial measurements have gotten cheap. So we have the opportunity to get high bandwidth, high sample rate, sub-meter accuracy with higher reliability. That's what we want to do. The challenges are overcoming outliers, nonlinearity, and doing this in real time. And the outliers is interesting to think through too. There can be situations where even though you have 40 GPS signals or GNSS signals, you're going under trees and past buildings, a high percentage of those in 1 second can be bad. Right? So even though you have many signals, you have many outliers. And you want to ensure that you're getting the accuracy that you state. There are many people looking at this type of thing, and I've listed a whole bunch of acronyms. I'll review these a little. RHE is Receding Horizon Estimation. SLAM is Simultaneous Location Mapping. Contemplative Real-Time, and Risk-Averse Performance Specified, where these are 2 things that I've been working on. But all these are optimization-based. They all come from a Bayesian perspective, and they all work with measurements over a temporal window. I want to spend a little bit of time motivating the ideas behind these 3 things, and I will have a little literature review comparing what's going on in the literature. But the main 3 points I'm trying to get across at the beginning here are, these are all optimization based, and they're all starting from a Bayesian perspective. And what we forget about is, so the Kalman filter is a standard method that's been used for state estimation, along with Moonberger observers. These things go back all the way to the 60s, and you usually see them presented as, here's 5 equations that implement the Kalman filter, and people forget this is optimization based. And it starts out with the given information being you have a prior, you have a linear model and a linear measurement, and when you go through the Bayesian argument, you get down to a cost function, which is you want to pick the x that minimizes the error, the residual in the measurements, and the residual in the prior. And when you go through and you solve this problem and you have a model, you optimize this and out pops this equation. And this is the standard Kalman filter equation in information form, right? And you can manipulate this to get in covariance form, and that's the way you usually see it in a textbook. But so for a linear problem with linear measurements, Gaussian noise, you get the Kalman filter. But then there are generalizations to the Kalman filter problem, and one of these is the extended Kalman filter. And the only real change in the extended Kalman filter is that now you have a nonlinear state transition and a nonlinear measurement model. You set up your Bayesian formula and you get down to this equation, and this equation is presented in a way where it's linearized. So the extended Kalman filter takes the Kalman filter method and extends it to a linearized nonlinear system. But the format of this in the linearized case is exactly the same as the previous slide, and you work through it and you get out the same equation in information form, but now this is a perturbation of the state. And so in terms of implementing this, what you're doing is you're taking the prior state and you're using the nonlinear state transition to get the prior for the current state. You solve these equations, you get a perturbation, you add the perturbation, and you go on. And so you're doing a nonlinear state transition. You use a nonlinear equation to predict your measurement, but the rest of it is a linearized Kalman filter. but it is the same optimization problem formulated in a Bayesian sense. And a method that you don't learn about much in grad school is the iterated Kalman filter, and you can find it in these two textbooks. But what this does is it goes back, where the previous slide, the extended Kalman filter, this was a linearized equation. You take one more step and you say, okay, if I keep my prior in my nonlinear transition, my nonlinear model, what I'm really trying to minimize is this. It's a nonlinear cost function. And I can solve this nonlinear cost function iteratively. I can iterate to find the x that minimizes this. And I'll get a better solution because in the extended Kalman filter, you linearize once, you solve, and you're done. Here you can iterate as much as you need to get convergence to the optimal estimate. And so when your measurement is very nonlinear, you'll get a better estimate. But now you can continue generalizing. You can go further back in time, and that's what many of these methods will do, and I'll try motivating that as we go through it. But the point here is all three of these are built on a Bayesian perspective. They're all built on optimization, even though we might forget the Kalman filter is built on optimization. It's just such an easy problem because it's linear that we can solve it analytically, where by the point you get to here, you're solving it iteratively. You still linearize to solve a nonlinear problem iteratively. So before considering further extensions, I'm going to present the motivating application, which is the type of state estimation problem that I like to look at. And so we're doing sensor fusion, and we're integrating two types of sensors. So one is inertial navigation, and the reason that you integrate these two types of sensors is that the inertial navigation gives you high bandwidth and high sample rate. If you take something like GPS and you try getting the full state, you would have to take derivatives. So you've got a trade-off between integrating an inertial measurement or taking derivatives, and integrating turns out to be a better process. So you can buy an IMU, inertial measurement unit, that has a high sample rate and a high bandwidth. That gives you two measurements, specific force and angular rate. And specific force is just gravity plus acceleration. You can integrate that to get velocity and position. You can integrate angular rate to get attitude, and you can combine it all together through a kinematic model, and you carry on. And so you have a kinematic model, so you have to think about what's the difference between a dynamic and a kinematic model. And a kinematic model, in and of itself, it's perfect. There is no model there. So an example kinematic model is the integral of acceleration is velocity, the integral of velocity is position. There is no error in that. The error comes in because you have sensor errors and you have sensor noise, and you have calibration errors, and you append all these things in the state vector, and that's what you have to estimate to get high precision and high reliability. But the kinematic model portion is very easy. You have this model and you have your IMU measurements and you integrate it in discrete time. You do that numerically, and you can propagate your state through time based on the IMU measurements at the IMU rate. And this operation, I'm just going to call this phi. Okay, so in later slides I'll be saying x at time tau I plus 1 is phi of x tau I. That's just numeric integration of the IMU state, and this is all straightforward. This has all been being done very reliably since the 1960s. The main new issue is that the IMU price point is getting low enough that we can afford this in commercial applications. So they're in quadrotors, they're in cars, they're in many different things, and so we can do this for commercial applications. So
this slide that you're on, talking about sensor fusion?
Yeah, this is the first slide on sensor fusion, right? And I haven't fused anything yet at this point, right? So we integrate the IMU through. Oops. So tangled up by losing the microphone. All right. So we integrate this through time. The pros and cons of this that require the sensor fusion are so we take the INS and we integrate it through time. This gives us the high bandwidth, the high sample rate. But integration is nice. It reduces high frequency noise, but it's bad in that it accumulates errors. And you have errors because you have calibration errors, you have initial condition errors, and you have so calibration errors and noise. So you accumulate all these over time, and that accumulation is without bound. And so if you just did this for a long period of time, you'd get huge errors. So you need to correct it. Thankfully, we know the error growth model very well. It's easy to characterize that, and that's the covariance propagation equations. But you have to bound that. You have to correct it with something, and that's where the sensor fusion comes in. And so we have what we call aiding measurements. measurements. And the aiding measurement examples are GNSS and feature sensors where features either vision or LiDAR. But so given that we knew the state and we know the model of the sensor, we can predict what the measurements are. And here in this slide, I'm using N for noise and E for outliers. And we carry on. So for each sensor, we have a model. We can predict what the measurement is, and we can form a measurement residual. We can do this for GNSS, and we can do this for features. The benefit of these aiding sensors is they have bounded errors. So for example, for each range measurement, if I'm doing differential GPS, I know that my error is bounded to 1 to 3 meters. So I can use that to correct the INS and bound the INS errors. The con is that all the aiding sensors are sensitive to the environment in some way, shape, or form. The IMU is insensitive to the environment, where GPS can be blocked by buildings or trees. Feature sensors can be blocked by something going by, or by lighting, or by weather, or other factors that can affect them. So they all have something that affects them. But when you combine these together, you get very nice features, and that's the sensor fusion approach. One other topic here. So I'm going to use 2 symbols. So tau is the sampling period of the IMU, which is small. T is the sampling period of the aiding sensors, which is usually large. Right? So you get many IMU samples per aiding sensor time change. So the standard approach goes like this, where if you're using a Kalman filter, your standard approach would be you have a prior, and you get an IMU measurement, and so you use your INS to integrate these equations to advance 1 IMU time step. Since the IMU time step is much smaller than that of the aiding sensors, you're going to do this many times. So you might do 200 advances of the IMU to get to the time of the next aiding sensor. So you've integrated this 1 step many times, and the symbol I'm going to use for that is B of capital U. So little u is 1 IMU time measurement, and big U is the set of all the IMU measurements that are between 2 aiding sensors. So from here to here, I have several hundred IMU measurements. I'm going to call that set U. And I'm going to do that because I'm going to be reprocessing the data. So I'm going to save all the data because I want to reprocess it. So if I'm going all the way from 1 aiding time to another, I have a set of IMU measurements, and I can reprocess the data. All right. So the standard EKF, you would start with your prior, propagate your state to here, and then at this time you have an aiding measurement. So you predict your measurement, you calculate your Kalman filter gain, you propagate, or you correct your covariance, you correct your state, and you go back and you're ready to start the next step again. And that's the standard EKF approach. And in doing that, you've conditioned on a whole set of stuff. So the posterior state at the end of the time interval is conditioned on the prior state back here, this full set of IMU measurements, the aiding measurement at this time, correct linearization of the system along the way, and the item that we forget is all fault decisions made up to and including this time. But the fault decisions or the outlier decisions that I make at this time affect which measurements I use here. All outlier decisions that I made in the infinite past affect my prior. If the prior is wrong, then my decisions that I make now are wrong, right? Because I might think I'm here very precisely when actually I'm over here with an imprecise thing because I made a wrong decision. All of those decisions are factored into the prior. Yeah.
So at the aiding moment, you're using Kalman filter to do the fusion.
So I'm not. I'm just giving you the traditional method.
Oh,
but,
okay.
But at this time, you would.
And then, but before that, those green jumps, those are also Kalman filter steps?
No, these are just the IMUs propagating the state. So when the IMU propagates the state for a millisecond, there's nothing to compare to.
Oh,
So you might have to do that 1,000 times to get to the next GPS to make a Kalman filter correction.
There's no measurement happening.
Yeah. So all these green steps, it's a very good point. The Kalman filter is only happening at the red. And so I indicate time K. The subscript K means I have new information. I'm doing sensor fusion.
Okay.
Where these are just the IMUs propagating stuff.
I see.
Right? And so when you think about this, at time K, when I'm doing something, I have N plus M constraints. I have N constraints from my prior, I'm a state, and I have M constraints based on the measurements, but I'm estimating N variables, so I'm left with M degrees of freedom. Based on those M degrees of freedom, I'm trying to decide which of these measurements are valid so I can go on. And we use this standard Kalman filter for many years trying to get things to work. And either it works fabulous or it blows up. Because once you make a wrong decision and you think you're here precisely and you're over here, then all subsequent fault decisions are wrong and you start drawing invalid measurements and your Kalman filter diverges. So you want to do a better job with outliers. So challenges here are the EKF is sensitive to the linearization point. In particular, the initialization of the attitude and the biases, because those things are, initially they're unobservable, but especially the attitude is a very strong nonlinearity. And then once you make your outlier decisions, they're irrevocable. You can't go and say, oops, I made a mistake 10 seconds ago, how do I fix it? Right? There's no way to go back. Okay, outliers we've already talked about quite a bit, and the covariance inaccuracy. Once your covariance is inaccurate, then you're using the wrong Kalman filter for the action you have, plus you're making wrong decisions. So these issues are all more easily addressed by considering the problem of how do I, instead of estimating the state at a particular time, how do I estimate the trajectory over a window? So we're trading a state estimation problem for a trajectory estimation problem over a sliding window. So in the sliding window approach, I'm going to let X with subscript L be the sliding window of the past L states. And notice this is the state only at the times when I have additional information. In between this, there are several hundreds or thousands of IMU times, and you're able to ignore that and solve this smaller problem. If you do this with L equal 1, you're doing the Kalman filter, the extended Kalman filter, the iterated Kalman filter. If L is bigger than 1, then you're doing receding horizon, simultaneous location mapping, CRT, or RAPS. And what you're doing is you have a prior L seconds back, you retain all of your IMU data over this window, and you have your kinematic model. So now you have a whole time window, and you can reevaluate. And that's why we call it contemplative. You can reevaluate. You can say, I think this set of stuff is good and that set of stuff is bad, or you can trade off and make different decisions. But what you want is whatever gets into your prior L seconds ago should be blessed. It is guaranteed to be free of outliers, because that's the starting point for this whole thing. So how do you make that happen is the problem we're trying to address. So the CRT approach, or when you do this over a window, you can, again, set up your Bayesian problem. And the problem is, so starting from a prior, so this should give a very slight extension of the iterated Kalman filter, because we're still doing a step with, or a window with only one measurement in it. But we have a prior, we have a state transition model, and we have the nonlinear measurement. And you set up your Bayesian problem, and so you're trying to maximize the probability of the measurements, the state transition, and the prior by picking the current and previous state, and you work through this in the normal way. So you can assume whatever noise distribution you want. Here I'm assuming Gaussian, so since I assume Gaussian, I end up with two norms, or Mahalanobis norms, where P is the initial covariance, Q is the state transition noise, and R is the covariance of the measurement. And I'm doing this with L equal 1 basically to show you the structure of how we solve the problem, but we really care about bigger windows. So this is a 2 norm, and we can go through and optimize this, and you're going to end up, so we're solving this nonlinear problem. It is nonlinear because we have a nonlinear state transition and nonlinear measurement, but each iteration is solved by solving a linear problem. So you have linearize, solve, do that until it converges and you're done. Each linearized problem gives you a set of residuals, a matrix that we'll be calling J, the Jacobian, and the perturbations that you're trying to estimate. As you solve this linear problem, you add the perturbation into the state to get a new state, relinearize and do it again until it converges. And along the way, you've got to make your fault decisions. After it converges, you extract the covariance so you can carry on to the next step. But so at each step, we're solving an iterative linear problem. Yeah.
So this is when L is equal to 1, are we estimating just xk or xk and xk minus 1?
Yes, xk and xk minus 1. So we're willing to change the posterior at the end of the last step, right? Because this still only has the measurement at the current time, but we're willing to adapt the posterior at the end of the previous time, right? So But you can see how this generalizes going back further. If I go back further in time, there will be multiple time steps, there will be multiple measurements, and I'll basically be adding and stacking up more residuals and more states. So this J will get more columns, right? But I can always do that, and by doing that, I can change my linearization point, and I can change my fault decisions. You know, if you think about a car is driving down the highway, and it goes under a viaduct. At the moment it goes under the viaduct, depending on where that aligns with the GPS measurement, your measurements could or could not be corrupted. But you get additional information when you come out the viaduct on the other side. And that helps you to decide what happened back there. And combining that information together, you get a better estimate of the state. And the same thing happens when you go by degrees, which happens all the time. Some measurements get corrupted. If I have to make decisions now and they're irrevocable, it's harder than if I can say, well, let's look at a window of what's been going on. How do I make my decisions? Right? Yeah.
So applying the sliding window will help to minimize the divergence of the common filter. Because you said like divergence happen because we cannot correct the previous state, but here you said that you will consider the correctness of the previous state.
Yeah, and we're going to take that even further backwards in time.
Okay.
So like the common filter can diverge for many reasons. Like if it only has one linearization. So for example, the heading of a car, if the heading is wrong, you might think you're going this way when actually you're going that way. The common filter cannot correct that because the linearization error is too big. For this, you would just iterate and the heading would come around to the right thing.
It will correct itself.
Once it's observable, and we'll have that example at the end. Right, so the common filter could diverge because of linearization error or outliers, right? An outlier is, or causes the state to be here when it thinks it's here. Well, then the linearization point is wrong. And if it can't correct it, then it diverges. Right, or the covariance is wrong, and so then it ignores all future measurements because it thinks it's here when really it's there. Right, so there's many ways the common filter can.
So this takes care of both the linearization as well as outliers.
Yeah, and I'll show you at the end the linearization works. Yeah.
So in this case, we're only allowing ourselves to modify xk minus 1, the mean of the prior, right? Not the covariance.
Yes. Well, and that's why I'm saying, so, you know, and eventually this is going to be back L steps where L is bigger than 1.
Right.
So to me, the goal is, as I make, you know, because you can't keep so the reviews that we get back on this type of stuff are very different from the controls community from the SLAM community. The SLAM community reviews will be, why do you ever throw anything away? Just keep the entire trajectory. Which you get, it makes sense for them in their application because they're also building a map. But it doesn't make sense in my application where I'm trying to sell on a cheap device like a smartphone or car manufacturers that are very cost sensitive. I can't keep the entire history of all measurements over all time because cars get driven a long time, right? But eventually I have to throw something away and say, my window's only this long. When I throw something away, I am then fixing this prior. I want to make sure that my prior is what I say is plus. There are no errors in the prior. So I'm going to be conservative in what I include in the stuff that goes into the prior. Because if the prior is wrong, that makes everything else hard. Right? You can still fix it, but it's hard. It's much better to be conservative.
So you assume the statistics are continuous, just a value.
Yeah. Well, let me get ahead a little more so we got more. This is really, if I do too long of a state, this just gets too big. So I'm doing L equals 1 just to show you the structure of the problem. So eventually we're doing a longer window, and I'm sorry for switching from L to K. I didn't have time to update the slides. But so, you know, we have a window. In this window we have K different aiding times, and I have the IMU data over this whole window, and I have a prior, and we call this the CRT window, right? And at the beginning of this window, I have a prior, I have all my IMU measurements, all of my GPS data, here I'm saying carrier, or pseudo-range and carrier phase, and my goal is to get an optimal trajectory estimate over the window. So now this vector is pretty big. It's K times NS. So NS is the number of states. So if I have a 15 vector, and I do this over 10 seconds, I've got 150 variables that I'm trying to optimize in real time, right? Because K is 10 and S is 15. If I'm doing carrier phase, I'm also estimating integers. And the pseudo range gives me actually about a meter, where if I can get those integers, then I get centimeter accuracy. But it's very risky because you're estimating an integer. If you're wrong on the integer, then you're off by 19 centimeters. So then you'd be saying I'm here to centimeter accuracy, but you're really here, or worse, another 19 centimeters away. So it'd be great if you could do the carrier phase, but it's also high risk. Right? So currently, the cars are not using carrier phase, but it would be great. But there's I have extra slides. If we get to it, I doubt we'll have time to talk about carrier phase, but you would like to then optimize this Bayesian problem over this window, and you've got this cost function that you want to solve to make it happen. Right? And so this problem has a nice history. So the first reference I know that's related is by Jazzwinski in 1968. He's a famous stochastic guy back in the day. And he's looking at this for a scalar problem. And he calls it, so he's showing his Kalman filter diverges for this problem. And then he calls it a limited memory filter. And he's showing that the limited filter works. It's one state. And he's probably doing this on paper or cards or something back in 1968 to show that this one problem works, and it was not real time. This is a simulation, but it's the same idea, right, all the way back in 1968. In the controls literature, this is called receding horizon estimation, and this came about by these guys, Muskie, Rawlings, and so forth in Maine. And their interest, so if you look at this is the same cost function that I just showed you, but what they were looking at is they phrase it as they want to minimize this cost function subject to a constraint, which is a dynamic model, and another constraint, which is measurements. But then the state, the process noise, and the measurement noise all have to be in certain sets. So they're looking at this from 2 points of view. The literature focused on stability of the state and feasible sets. And the reason they cared about this is because they were doing problems in chemical process control. And if they did the Kalman filter, they might get something like a negative concentration, which had no physical meaning. Right? Because the Kalman filter would make a correction, the concentration would come out negative, and everything would crash. So they rephrased this, and they said, okay, we're going to solve this problem that the Kalman filter is solving over a window, but we're going to force our states to be in a set that we know it can be in. And so they solved that. And their literature, all these papers except for one, focus on chemical processes where the process is slow, and they want it to be in a certain set. This paper by Grizzle is working on robotics. And Grizzle's stuff is great, and he's doing discrete time. It's very similar to what we're doing, and he's trying to make sure that the robotic state is realistic, so that he does walking robots. He doesn't want the robots to fall over. It also is the SLAM literature. The SLAM literature comes up, so SLAM is simultaneous location and mapping, and it ends up when you get down here, they've got the same formulation. When they start back here, they're not. They just know they want to simultaneously figure out where is the vehicle and build a map. And in the early papers, the papers are trying to sort out what is the statistical relation, what is the problem, how do we formulate the problem well. And down in here, they're getting into a nice formulation of the problem and realizing the computational load is huge. We might be able to solve this, but we need to back off and do some approximations. Eventually they get to convergence results saying that the cross correlations are huge because the early algorithms threw away all the cross correlations. And eventually they get a nice understanding of the probabilistic problem in different papers like this Thrun one. It ends up being the same formulation that we're working with. And then all the ones I've colored green here, they're focusing on computational solutions. Really nice computational solutions, and they give the software away for free. And we can use the exact same software for doing what we're doing. And some of these papers they're just really nice papers. They come out of mainly the computer science literature. And all the way back here, people were telling me the SLAM problem is dead, it's solved. This is a great paper, it's done. But it's been going on, different aspects of the problem for another 20 years, and they're really nice papers that come out of it, and the literature all fits together very nicely. And we use those algorithms to solve the type of problems that we're doing. So the results that I'm going to show as we go on here, they do use GNSS and IMU. So a couple words on GPS and global navigation. So there's two measurements, one is code and one is phase. And I'm doing everything differentially. So in differential GPS, you have a base station and you have a rover, and the base station calculates a correction, sends it to the rover, and the rover uses it. and it eliminates what are called the common mode errors. So you're left with this simpler model where you have your nonlinear measurement, which is range, plus noise that you can call Gaussian, and it's about 2 to 3 meters in error. And then you have the phase. And the phase I already talked about, it's the same nonlinearity, which is a range function plus an unknown integer, and then noise. But this noise is centimeter level. So if you can get that integer, which is a bias, and estimate it correctly, you can get centimeter accuracy. It turns out that so we're going to integrate this. This is our state. Our state is position, velocity, attitude, the bias on the accelerometer, and the bias on the gyro, plus clock errors depending on whether we're doing single or double difference. We also may have to estimate the integers and other calibration factors to get this to work. When you make a measurement, you choose a satellite, you have a state space with 15 dimensions, and each satellite corrects one linear subspace of that airspace. If you've got 4, you can show the system is observable once the vehicle is moving. When the vehicle is sitting still, there are certain states, the yaw and the biases that are not observable. You need a diversity of aiding measurements to get observability, and you need outlier and incorrect, the ability to detect and throw out bad integers. These are challenging because you get frequent loss of locks and possibly corrupted measurements, because as you drive by buildings, you get multipath. As you go under trees, the foliage affects the quality of the measurements and so forth. All the math I'm doing, you can also do with vision, LiDAR, and so forth. All right, so back to the problem we're solving. We're solving over this window. The pro is we're going to be able to detect and accommodate, we don't detect, we'll be able to accommodate outliers. We'll do a full nonlinear optimization so we can correct the initial linearization error. The con, of course, is going to be computational load, because you're solving a nonlinear optimization online. And as I said earlier, we have this residual vector, and it has parts. The first part is the prior. This is all the state transitions, and it's a nonlinear state transition, and then you have your pseudo range and your carrier phase measurements. And you've got the stack of stuff you're trying to minimize the normalized residual after compensating for the noise. And depending on which measurements you use, you get different levels of accuracy. So if you just did the IMU problem, here you don't have anything to bound the error in the IMU, so you would accumulate an infinite amount of error. So of course you don't do that. If you solve the pseudo-range problem, you get this real optimization where you're estimating the trajectory, which is a set of real variables. Now you get about a few meters of accuracy because you're just using pseudo-range, where if you can use the carrier phase, you now have a slightly harder optimization problem, because now you're estimating the real state plus the integer n, which is the number of integers that the wavelength is biased by, that you would get centimeter accuracy. All right, so we have these different things which give us the different components of the residual, and we want the, so you take the log of the Bayesian cost function, and you get a sum of squares cost function, and we want to solve this. And it has the generic structure at each iteration. It has the structure J times delta x equals B, and we want to get delta x. And delta x at this point has real variables and integer variables. And I want to talk about how we solve this integer estimation problem. And so I'm going to divide J into 2 parts. So I think I skipped a portion of one slide that talked about the number of outliers, but I'll come back to it if we have to. But we're going to break this J up. So J is going to have 2 sets of columns. A is the set of columns that multiply the real part of the state, and B is the set of columns that multiply by the integer. And I'm just breaking this up because on the next slide I'm not going to have all of this. I'm just going to have A and B. So we have this cost function, and it comes down to minimizing Jx equal J delta, picking delta x to minimize the error between J delta x and B, and J as A and B as columns. So we have this cost function we want to optimize, and we want to simplify. So if we do a QR factorization on the matrix A, then you get a nice structure, because this matrix Q is unitary, and I'm going to break it into 2 sets of columns, QA and QA bar, and QA multiplies an upper triangular matrix R, and QA bar multiplies the 0 rows. And you do this because when you substitute this definition of A into here, you get this cost function with 2 parts. And if you look at this first part, if I give you an integer n, you can always pick z to make this term 0, because RA is full rank. So I can always pick z to make this term 0. Well, if I can always pick z to make this term 0, the whole problem comes down to find the integers n that minimize this term. Okay. And there's two different ways of solving this. Chang and Jua up in Canada came up with an algorithm called Miles, and DeJong and Tiberius came up with the Lambda algorithm, and I'm using the Miles algorithm. But at this point, this is software you can download, and it goes through and it finds the best integer n. Once I have n, I can substitute it in here and solve for z, and that's my state correction. And I can correct my state and carry on and see that work. And so we're going to look at this, and in this example, my k, the length of my window, is the entire trajectory. So this is solving over 600 and something minutes to get this is how we come up with the ground truth estimate that I compare my real-time solution to. This is not real-time, but this is driving around the UCR campus. And so there's trees along, so the pictures here, the student is showing that there's trees along parts of the campus. Here we're going by the engineering building, and you can see there's trees and buildings. And so these things are causing the number of satellites, which I've plotted at the bottom. Sometimes it's 8, but sometimes it's getting down to 2 or 3 satellites. And we want to solve this problem and show that we can get the accuracy that we're talking about. So this is computed accuracy. So there's theoretical accuracy and there's real accuracy. This is the theoretical accuracy. When I'm done solving that problem, I can pull out what I think the covariance is. And if I plot what I think the covariance is, from the pseudo range, I get down to about 0.8 meters, 0.6 meters, 0.5 meters. When I solve the integers, I get down, this is 1 centimeter, 2 centimeters, 3 centimeters. So we're keeping about 2 centimeters of accuracy, except at times when the GPS satellites go away and the problem's not observable, and then you accumulate error. Worst case here, the top of this is about 8 centimeters. So here we are theoretically computing that we're getting about 2 centimeters of error for the majority of time, with 10 centimeters of error when we don't have enough satellites. Where this is more the accuracy that we're actually getting. We look at the residuals of the estimation problem and see how big are the residuals. And up here, we start out using just the code in the pseudo range and the Doppler, and you see this point is -1 meter, 1 meter, so we're getting about 1 meter of accuracy. And then we estimate the integers, and down here we have the carrier phase residual, and the standard deviation is 8 millimeters. Right, so once you get the integers, you do get down to centimeter accuracy. And again, this is the ground truth for the entire trajectory. It will not be quite as good in real time because you just don't have as much data. And so now to do this in real time, of course, we can't do a 600-second window. So usually here we're doing about a 10-second window. The mathematics of the problem is identical though, and we're trying to solve it. And I have 2 slides here talking about nice things that pop out of this. One is bias initialization. So when you're sitting still, the bias and the attitude are not observable. Once you start moving, those things become observable. And the first slide here is comparing the green is the Kalman filter estimate, and you can see it's wandering around even 600 seconds into the simulation. This is exactly the same data. I'm running the Kalman filter and the CRT algorithm on exactly the same data. The blue is the CRT algorithm, and you can see as soon as the vehicle moves at 20 seconds, it zeroes in, and it basically keeps it constant the rest of the time. The uncertainty estimates are about the same. So having the window gives you a much better estimate of bias. This slide is talking about yaw initialization. And here what we did is we purposely, so the vehicle is pointing north, and we told the state estimator it's pointing south. So we purposely gave it 180 degrees of initialization error. So when the vehicle starts driving, the vehicle moves north, where the state estimate moves south, right? And the Kalman filter cannot correct 180 degrees of linearization error, and the Kalman filter blows up. And what you see goes on here, so this is the ground truth that I got from the stuff I just showed you. It's sitting, pointing north, and keeps that. And this is the state estimate starting out at 180, and it stays constant for the first 20 seconds because the car is sitting still. As long as the car is sitting still, the estimator has no way of knowing that its direction is wrong. Once the vehicle accelerates, you can see that it basically drops down in one iteration, and then it has whatever 40 degrees of error. By the second it's zeroed in and it just carries on. This is great because this saves the manufacturer a sensor, because the previous way of doing this is you have a magnetometer, and you measure the magnetometer's yaw, and that gives you enough accuracy to carry on with the common filter. So this is a very nice result. By doing this over a window, you make a sensor go away, and you can still get the convert the stability of the algorithm to carry on. So this removes the linearization error from the reasons for divergence. This is looking at the performance of the algorithm as I increase the window length. So the first one here is the extended common filter is the blue, and then the IEKF, and then L equals 5, 10, 15, 20, sorry, 10, 20, 30, 40. As you increase the length of the window, this is showing the cumulative distribution function of the errors. Remember, I have the ground truth trajectory, so I can compare it each time the error. And what this is saying is that, and again, this is the exact same data, just rerunning the algorithm. So the EKF, so this is a meter of error. The EKF is getting a meter of error about 90% of the time, where once you get up to time window L equals 10 seconds, you're getting a meter of error 100% of the time. So just by changing the algorithm, we go from 90% sub-meter accuracy to 100%, and this is about a factor of 10 improvement in accuracy as we increase the algorithm. And the reason that happens is both you're able to correct the linearization error, but also you're able to remove errors. And so this is looking at the rock curves. So here as in the common filter, we just have a threshold. As you change that threshold, you get different probabilities of false alarm or correct detection. And when you have more data in the window, you can do a better job because you have more degrees of freedom removing that. I want to get to one other result here, so I'm going to skip through this section. But this is a paper that came out recently, and we found very interesting. And what it did is it tried to find the maximal subset of the available measurements that are consistent with the model. And that was very interesting, and it introduced a vector B that I'm going to talk about on the next slide. We saw we could use that to do what we wanted to do for a long time and couldn't figure out how to do, which is how to choose a subset of the measurements that have minimum risk that guarantees that we achieve the spec. And the way this works is the cost function we previously had looked like this, and we introduced a binary decision vector. So it's a vector B that has as many components as we have measurements, and the elements are 0 and 1. And from this, I can make the diagonal of B, which is a matrix, and I can put it in my cost function. What this allows you to do now, if B is 1, this measurement is in. If B is 0, the measurement's out. All right? So now I can set up a cost function having this in there. And if you look at this cost function, you can always make it 0. Because I can make all the B's 0, which wipes out this term, and I can choose the state equal to prior, and I've minimized my risk. But I have no measurements on accuracy. So what you do is you add in, so we have the cost function that's in there, and we require it to use enough measurements to satisfy the spec. So now this is risk. If this is big, I have high risk. If my cost is low, I have low risk. But it has to achieve the spec, so it can't turn off all the measurements. And this gives nice, interesting results. And you can go through and set up an algorithm to solve this. I'm not going to go through it. I'll be glad if we've got an hour after this, I can talk you through the algorithm. If you're interested, I want to make sure I get to the results. So again, this is comparing the Kalman filter, so NP Kalman filter, Neiman-Pearson Kalman filter. So if a residual, normalized residual, is bigger than 3 standard deviations, we throw it out. So if you use all the data, you get, so this is horizontal position error. If you use all the measurements, you get this blue curve where your horizontal position error is horrible. And again, I'm picking out a bad section of data where we're going through trees. So the trees corrupt the data, you get really bad measurements if you use all the data. If you use the EKF and you use measurements that are less than 3 standard deviations, you get this red curve for horizontal position error. Where if you use this algorithm that's minimizing the risk, you get the green curve, which is lower. You're minimizing the risk at each time step, but you're guaranteeing that you use enough measurements to satisfy the spec. And if you look at norm of the position error, where the Neiman-Pearson thing has got errors all the way up to 8 meters, this one has worst case errors up to 4 meters. All right, so it's choosing the lowest risk set of measurements to make things happen. This is looking at the same error a different way. And what's nice is that it also gives you a feasibility measure, right? It's an optimization problem. It will tell you the problem is feasible or it's not. Well, if it's not feasible to meet the spec, you should be telling the driver to hold the steering wheel because you know you're not meeting the spec. but it also tells you when it's feasible. So the green curve here is when it's feasible. So if one of it's feasible, 0 otherwise. You can be in a situation where the problem is feasible, but the risk is very high. And so you're getting two things very useful for telling the driver to steer the wheel. Either the problem's not feasible, or it's feasible, but it's high risk. Right? And you get both of those things coming out here. So when the risk is high, or the GDOT's high, or it's infeasible, you tell the driver to drive the wheel. Otherwise, it's showing down here. So this is accuracy. So the spec is we want to be less than a meter 100% of the time. Again, the red is the common filter. The blue is the risk-averse approach. The red is doing comparable to the blue, other than when things get risky, and then the RACS approach is better. The risk is always less for the RACS approach because you're minimizing risk in the cost function. All right, and I'm going to skip this slide. It's basically saying there's a lot more signals that are available that are currently being considered, which makes this kind of stuff more important. So in making the connected vehicles and autonomous vehicles commercially feasible, cost is critical, real-time observation is critical, and risk is critical. And being able to increase trust by making risk decline is really a key goal, along with cost. The algorithms we're coming up with are just changing the algorithm. Often vendors are willing to spend an extra couple dollars on a better IMU, but they don't consider spending a couple extra dollars on the CPU. And the CPU, spending a couple extra dollars allows you to do a better algorithm. And we're showing that just changing the algorithm gives you better performance for the exact same data. So we're trying to motivate that. A challenge in industry is people in industry often don't have the optimization background to understand and implement the algorithms, but they like the results and the type of things that we get out of this. So sliding window estimation allows trade-offs between computational load, accuracy, and reliability. It allows you to validate past decisions that you've made and remove decisions that you find are faulty. It allows you to correct initial conditions and allows new formulations, and there's new formulations coming out in various literatures, including the SLAM, the RHE, and the control system literature. And the two that we've been working on recently are the risk-averse performance specified and the contemplative real-time. They build on the RHE and the SLAM literature. So I'll stop there.